explored Newton's laws and the fact that if there is a force acting on a rigid body, it causes acceleration on the body. Now, let me explore together with you another aspect of what a force can do. So, suppose there is a planar rigid body. Suppose there is a planar rigid body and it's hinged at the point O. This is a planar rigid body, and say it's hinged at a certain point O. This planar rigid body is hinged at a certain point O, right? So hinged at O. And say it lies in the plane of the board. Now, if at a certain distance, perpendicular distance d from O, if at a certain perpendicular distance d from O, we apply a force F. We apply a force F. D is the perpendicular distance of O from the line of action of the force. What is this? This is the line of action of the force. Line of action of F. Right? Now what this F does is it causes, realize that this F causes the body to rotate in this sense. What sense? An anti-clockwise sense. Anti-clockwise sense. This causes the body to rotate in an anti-clockwise sense. Very clearly, what has this force done? This time, realize that it has produced what is called a turning effect. There is a turning effect produced by this force. There is a turning effect produced by this force. Right? And this turning effect in this case is anti-clockwise. ACW henceforth is anti-clockwise. There is a anti-clockwise turning effect produced by this force. Now, one thing, if the line of action of this force passed through O, the hinge, if the line of action of this force passed through O, the hinge, in which case very clearly D is 0, in which case D is 0, then the turning effect, there is no turning effect. There is no turning effect. Right? Which means for a given F, if the line of action of F passes through O, it produces no turning effect about O. It produces no turning effect about O. Right? No, so I'm talking of no turning effect about O. Also realize that if I increase D, right? Say if D becomes 2D, if D becomes 2D, then the turning effect doubles. If D becomes half of D, right, then the turning effect halves. If D becomes 0, the turning effect becomes 0. Yes or no? That means the turning effect produced by a force about a point, the turning effect produced by a force about a point will depend on the perpendicular distance of that point, from the line of action of the force. This is the line of action of the force, and the turning effect produced by F about O will depend on D, the perpendicular distance of O from the line of action of the force. If I increase D, the turning effect will increase. If I decrease D, the turning effect will decrease. Yes or no? Right? Now, so for sure, for a given F, the turning effect will, about a certain point, will depend on how far that point is from the line of action of the force. That means the perpendicular distance, D. Also, do you realize for a given D, if I double F, if F becomes 2F, then also the turning effect will double. Turning effect will double. That means turning effect then is proportional to the magnitude of the force and proportional to the perpendicular distance of the line of action of the force from the point O. Yes or no? Right? So, the turning effect then about O is proportional to how far O is from the line of action of F, is also proportional to the magnitude of the force F, is also proportional to the magnitude of the force F. So what we define now is a quantity which is set to measure the turning effect of a force, which we call the moment of the force. Moment of the force about O as the product of the force into the perpendicular distance of the line of action of the force from the point O about which we are measuring the turning effect. Now, from common sense, what you can do is you can evaluate the sense of the turning effect. In this case, if O was the hinge and if a force was applied like this, would you not expect that this body would rotate anti-clockwise? Right? So the turning effect for the figure drawn, the turning effect of F about O is anti-clockwise. The turning effect of F about O is anti-clockwise and has a magnitude F into D. That's called the moment of the force. About O. Yes or no? Right? Now, suppose the same rigid body, the same hinge O, and now I apply a force F. Which is at a distance D from O. This time, would you not want to believe that this body, if I apply a force F, this body would want to turn in this sense, which is a clockwise sense. Right? The magnitude of the turning force in this case is F into D. Yes or no? Right? And we say that the moment of the force about O in this case is F into D, but clockwise. Right? So, the moment of a force about a point could be clockwise or it could be anti-clockwise. So we are talking of a planar situation, and therefore clockwise and anti-clockwise would be enough in as far as the direction or the sense in which the rotation is proposed, right? Or the turning is proposed, right? Now, suppose there was a rigid body like this, and this was the hinge. It was hinged at some point O, right? And at a distance D from O, if I apply a force F, what would this force do? This would turn it in this sense, would produce a anti-clockwise moment. We say it's an anti-clockwise moment. Anti-clockwise ACW is anti-clockwise moment about O. And that's going to be F into D. F into D is the anti-clockwise moment. So it would want to turn this rigid body about O in an anti-clockwise sense, right? Now, suppose at a distance D now, I apply a force F this way. Right? Now, what would this force do? This force would produce a moment about O, which would once again be F into D, but this time it's going to produce a turning effect which is clockwise. A clockwise turning effect is produced. So this is an anti-clockwise turning effect. ACW is anti-clockwise, and this, and this produces a clockwise effect. And do you realize that both these moments are equal in magnitude? One is anti-clockwise, the other one is clockwise, and they would cancel off, and there would be no net turning effect. There would be no net turning effect. That means if the clockwise moments are equal to anti-clockwise moments, if the clockwise moments are equal to anti-clockwise moments, then there would be no turning effect produced, right? That means what we can do is we could even assign signs, in the sense, if there were number of forces acting, we could say all forces that would want to produce anti-clockwise turning effect positive, all clockwise turning effects or all anti-clockwise moments negative. I'm sorry, all anti-clockwise moments positive, say, and all clockwise moments negative, suppose, right? Then what we say is all anti-clockwise, so F into D is the anti-clockwise moment, and then clockwise moment is minus F into D, and they cancel off. So the net moment produced is 0. There is no net turning effect produced. There is no net turning effect produced about O. This body will not turn about O in this case, because the anti-clockwise moment is the same in magnitude as the clockwise moment. If I assign signs to it, then the algebraic sum of the moments, this is the algebraic sum of the moments about O, that turns out to be 0. Algebraic sum of the moments about O turns out to be 0. So suppose I had a situation like this. Say this was F1 and this was D1 and this was F2 and this was D2, right? And I want to know what's the net turning effect, the net moment about O. I want to find the net moment about O. Net moment about O. So again, we say all anti-clockwise moments positive, all clockwise moments negative. Or it's your choice. You could just do the other way around. You could say all anti-clockwise negative and all clockwise positive. Does not matter. But let's look at the algebraic sum of the moments about O. Let's look at the algebraic sum of moments about O. So anti-clockwise F2 into D2, F2 into D2, anti-clockwise moment about O, positive. F1 produces a clockwise moment about O, it produces a clockwise turning effect about O, so that's negative, minus F1 into D1, right? That's the algebraic. So what we have chosen in this case is all anti-clockwise moments positive, and all clockwise moments negative. So this is the algebraic sum of clockwise and anti-clockwise moments. This is anti-clockwise, this is anti-clockwise, this is anti-clockwise, so positive, and this is clockwise, therefore negative. So this is the algebraic sum of the clockwise and anti-clockwise moments, where anti-clockwise for this situation I have chosen positive and clockwise negative. Now, if this turns out to be positive, if this number turns out to be positive, then the net moment about O is anti-clockwise. Net moment about O is anti-clockwise. If F2 into D2 minus F1 into D1 turns out to be negative, clockwise moments I have chosen negative. That means the net moment about O is clockwise. So net moment here is clockwise. The net turning effect is clockwise. That means if this is less than 0, then this body would turn in a clockwise sense. If this is greater than 0, it will turn in an anti-clockwise sense. And if F2 D2 minus F1 D1 is equal to 0, then there is no net turning effect produced about O. It will not turn at all. It will no turning effect. No turn at all will be produced. Because algebraically, because the magnitude of the clockwise and anti-clockwise moments are equal. The magnitude of the clockwise and anti-clockwise moments are equal. So no turning produced if the clockwise moments become equal to anti-clockwise moments. Yes or no? Right? Now, now, I could have had multiple forces. Say, this is O. There is a force F1 like this, say D1 at a distance D1 from O. There could be F2 like this at a distance D2 from O. There could be F3 like this, which is at a distance. There could be F3, say like this, which is at a distance D3 from O. Then notice that F2 about O, O is the hinge, produces clockwise turning effect or clockwise moment. And how much will it be? It's going to be F2 into D2. What does F1 do? F1 produces about O an anti-clockwise turning effect, and of magnitude F1 into D1. What does F3 do? F3 produces an anti-clockwise turning moment, which is F3 into D3. Right? Suppose I chose all anti-clockwise moments as positive and all clockwise moments as negative. Then the algebraic sum of the moments, what's going to be the algebraic sum of the moments about O? Okay, so F3 into D3, F3 into D3. What's that? That's anti-clockwise. F3 into D3 is anti-clockwise, so positive. Then F2 into D2, clockwise. The turning effect produced by this force about O is F2 into D2. So minus F2 into D2. Right? And then what about F1? F1 again produces anti-clockwise turning effect about O, and of magnitude F1 into D1. So F1 into D1. So that's the net moment produced about O. If positive, then the net turning effect would be anti-clockwise. If negative, then the net turning effect would be clockwise. If equal to 0, then there would be no net turning effect. If the algebraic sum of the moments about O is 0, then there would be no net turning effect produced about O. And we say that the algebraic sum of the moments is 0. So this could be positive, this could be negative, or this could be 0. For no net turning effect, the net moment about O must be 0. Yes or no? Right? So in a given situation, for a, let's say, planar rigid body, there could be forces acting at different points of the rigid body, at different distances from a proposed hinge, and if the algebraic sum of the moments about the hinge or about a given point is 0, then we say that there is no net turning effect, and we say that there is, in a certain sense, the body is not turning clockwise or anti-clockwise, right? If the algebraic sum of the moments is 0, that means all the clockwise moments balance all the anti-clockwise moments. There is no net turning effect produced on the rigid body. Yes or no? So that was an important consideration. So moment of a force about a point, measures what is called the turning effect produced by that force. And how do you do that computation? You multiply the force with the perpendicular distance of that force from line of action of the force, perpendicular distance of the line of action of the force from the point O. Right? That's what you do. Product of the force into perpendicular distance of the line of action of the force from the point O. That's how you measure the moment of a force. Yes or no? Right? Now, another very important thing is, suppose this is a force F. Say this AB, this length AB represents a force F. Suppose this length AB represents a force F. And I want to find the turning effect produced by this force about O. All right. So say the perpendicular distance of O from AB is D. Right? Then what's the moment produced about O? In this case, of course, you can see it's anti-clockwise. Anti-clockwise moment is produced about O, and it would be of magnitude F into D. So would you again not want to believe that F is measured by the length AB? F is measured by the length AB, and this length is OP. So base into altitude, would you not want to believe that this is twice the area of triangle OAB? This is twice the area of triangle OAB, right? So that's a geometrical way of exploring the mathematics here. So if there is a force F represented by AB, by the segment AB, and O is a point about which you want to measure the moment of the force, then twice the area of this triangle, will give you the net turning effect or the moment of this force about O. Now another important aspect is, suppose there is a force P and there is a force Q acting on a rigid body, right? Suppose these are two forces, and then using parallelogram law you can find the resultant of these two forces. This is the resultant R of these two forces, right? This is the resultant R of these two forces, right? Now the important thing is if R is the resultant of these forces, and if O be any point, then the moment of P about O plus the moment of Q about O will be moment of R about O. That's the important thing, right? So moment of P about O plus the moment of Q about O will be the same as the moment of R about O. That's important to understand, right? The moment of, suppose I had, and if there were multiple forces, say P1, P2, P3, P4 having a resultant R, then the moment of P1 about O plus moment of P2 about O plus moment of P3 about O and so on and so forth will be the same as the moment of their resultant about O, moment of their resultant about O. That's an important thing that we will use again and again, time and again. Thank you so much. Bye-bye.